Hi, thanks for giving me the chance to tell you what we've been up to on the Honeysuckle Creek watershed study this year. It's been very exciting. We've learned a lot about this patch of ground draining into Burt Lake, and I really appreciate that I have the chance on the agenda, among everybody who's here, to talk for a little bit about our exciting research. Where do I point this? Okay. All right. The past year, I've broken this into a few categories. We've put a lot of things out in the woods, leaving more of the watery end of things to Paul. We've collected a lot of data as a team, and we've submitted some proposals to fund the work that we're doing there. I'll speak in more detail about each of these categories, so just an overview of where we're going. A number of us spent quite a lot of time and calories and sweat in the woods this spring and summer and fall, deploying components to build a wireless sensor network. This is something that's been developed by Bronco Kirkes, and we had a whole bunch of people come and give their time pro bono or for educational purposes only to deploy these units, which consists of a solar panel, a battery, a data logger. In some cases, there are wireless network cards that link these nodes to one another across the watershed. To remind you, Honeysuckle Creek watershed, it's about 2.5 kilometers from the top of the Pelston Hill down to Burt Lake. Over about here is Carp Creek, perhaps a little farther this way. So our network nodes span a wide range of elevations, topographic positions, ecosystem types, and so on. And at each of these nodes, we have deployed sensors to measure soil parameters, meteorological variables, and in some places, these nodes are able to be outfitted with devices that measure water level, whether in piezometer wells or flumes. At some point, our data loggers will record data continuously, and some of those data will be streamed real-time to the World Wide Web, which could prove useful for desk-based data analysis, whoever wants to go in the woods again, and also perhaps remote learning opportunities for students elsewhere. What we're going to be doing with the wireless sensor network in 2016 is to add the sensors measuring water levels and piezometers and stream flow, and to bring the system online so that we can actually view the data as they come in. In the spring, Jason and Paul and I had enough of cabin fever, so we decided to get our hands on some galvanized pipe and go out and pound some shallow sandpoint wells into several of the, to a couple locations along the reach of Honeysuckle Creek proper. Honeysuckle Creek, as I may have mentioned last year, or Paul has described, is not a well-behaved creek. In some places, it's just seepy earth. In some places, it is a channelized stream. But towards the end of being able to collect samples for chemical analysis and also monitor the height of the water table, we pounded several sandpoint wells. The results I have to tell you so far is that I drank the water and it tastes okay. It tasted better in May. I think the qualitative results are important, actually. In May, it tasted like iron, and in August, it tasted like sulfur. And I think this says something very logical about the biogeochemistry of what's happening in that watershed. We have a spring pulse of iron and aluminum hydroxides bound to organic matter, moving carbon through the shallow groundwater. By the time the water table has lowered in the summer, there's some sulfur-reducing processes going on, and I don't recommend drinking it. One thing I'm very curious to hear about at this meeting is the results that Rich Fiorella, a grad student, has regarding the oxygen and hydrogen isotope ratios of this water, which will give us some estimate of its residence time within the 2.5 kilometer stream and water tables. We have some data from Tim on the dissolved organic carbon concentrations. Just to point out to those of you who deal in such things, there's not much dissolved organic carbon in this stream. It's a very it's a high pH, and even at just 2 meters depth, we're looking at concentrations of the order of 1 milligram per liter, a lot lower than lake water or most types of stream water. So anyway, we might do more of this, but we'll make it look a lot easier. In this summer, Lizzie Michelson and Nick Van Dyke gave a lot of time to helping me measure soil moisture. Katie Hoffmeister, a grad student at Cornell, has helped to develop a sampling strategy towards validating spatial models of soil moisture and saturation that she makes. And we identified a sampling design of transects running north to south across the extent of the watershed, 99 sample points that we measured over the course of the summer and the fall, July to November. I won't go over every row here because who likes exhaustive data slides, but to point out that the Landscape Ecosystems Framework continues to be a great way to look at this landscape. We find very logical differences in the soil moisture content of the top 20 centimeters of the soil as a function of ecosystem classification. A couple to point out, everybody in this room knows type 59. It's good aspen. The ecology labs that climb the Pelston Hill and go to the soil pit off to the south of Riggsville Road, that's type 59. Banded outwash over till. Mesic aspen, we have pretty good sampling of dunes. There are more dunes than I ever realized perched on this moraine with its recessional lake features. And then as you descend down the moraine closer and closer to Burt Lake, you go through successively less and less outwash mantle on top of that till through what I would call a mesic till, type 113, aquic till, and then type 118, the channel wetland, and increasing soil moisture until you hit the Lake Nipissing Plain swamp, type 55. And basically it's just saturated down there all the time. But to point out, we find good differences between these ecosystem types, and there'll be a good basis for the mapping that Katie does. If I talked to you in the cafeteria this summer and looked very dirty, it was because I took a lot of soil profiles. And a whole bunch of people helped with that, of course, I'll acknowledge at the end. But we've now observed as a group over 100 soil profiles on the 100-hectare watershed and have approached this in the ecosystems classification framework as well. And it's complicated but not confusing out there. There's a lot of local spatial heterogeneity. That's a place where the ice went to die, so you never know where you're going to find a dune versus outwash, but there are consistent patterns in things like the depth to the till layer that restricts water movement down and causes Honeysuckle Creek to exist, the depth of the water table, and also redoxamorphic features as indicators of wetness in the sand cap on top of the till. In 2016, Katie and I and the team will take another 50 profiles. We'll use those to refine her spatial models to create a very local, high-resolution soil map of the area. And we'll build on the data sets we've started that will pertain to the carbon and mercury stocks in the soils. Other people, of course, were active throughout the summer. Bob Fahey and the Forest Ecosystems class, a couple class groups measured forest composition and biomass in a couple of the ecosystem types. Tim Veverica and Rich Fiorella, I've mentioned, have run soil solutions and also groundwater and stream water samples for chemistry. Jim Lemoyne, as always, does a hell of a general's job leading the army of European nudists, which is what we call the Europe enrolled undergraduates, undergraduate research opportunity, and all of us new acolytes are nudists of one sort or another. And they did a great job of measuring the thickness of the organic deposits in the type 55 Lake Plain swamp. That'll make for a fantastic paper about carbon and mercury stocks in that most carbon and mercury rich portion of the ecosystem. Jason's been processing the LiDAR data from the spring flyover to give us an improved digital elevation model as well. Proposals, let's see, a small one that I put in at Paul's prodding and all the information Paul gave me to acquire pressure transducers to measure water depth in the piezometers and stream flumes. Paul and Valeria Ivanov and Kate Heckman, a collaborator of mine at the Forest Service in Houghton, Michigan, we submitted an ecosystems pre-proposal to the January solicitation, and that one I led. Paul will be leading a low-temperature geochemistry proposal to NSF Geo sometime during this remaining winter or spring. I don't mean to take credit for others' work. I'm just the one that gets to do the talking, kind of like Paul said. So a lot of people have been involved in this and have made their own kinds of contributions as we get this study up and running. And I won't call out everybody here, but just to point out that every one of these people has done something important to this project, and I am indebted to all of you. Thank you. And please, if you have any questions or comments, save them for Tim, who's going to follow Paul.
Might be wise to ask them directly to Luke.
How much time?
10 minutes.
Oh.
And that advances.
Okay.
Let's say 8 to 10.
Hi, everybody. Thanks to Luke for giving such a great introduction. That way I can just give data slides and miscellaneous things. So I've been at the biostation now for about 2 years. I'm the aquatic scientist, and I'm really focused on, for one, understanding the mercury problem in northern Michigan, which is a problem of the atmosphere that affects aquatic ecosystems. So the Honeysuckle Creek watershed drains into Burt Lake, which is one of about 900 lakes in Michigan that's on this list of federally impaired lakes because of too much mercury in fish. So aside from great support from the biological station, we also received funding from the USDA for this project to establish this watershed study to look at the retention of mercury in forest soils. There's no way that I could tackle this problem without the great collaboration of Luke, Jason, Jim, and everyone else that's chipped in. It's been really a rewarding experience to come to the biostation and have so much expertise on forests. And it's really broadened my research approach. To understand why forest management practices could be important for mercury cycling, mercury levels in fish in lakes, I put this up as an example. So 2 lakes, Vincent Lake, which is just north of Douglas Lake, Weber Lake, which is just south of Burt Lake, near Wolverine. These are sediment cores from these lakes. It's mercury concentrations with depth in these sediment cores. And what we can see is for Vincent Lake, which has a very small watershed for its lake, so the ratio of about 3, what we see is something that we see in just about every lake. Actually, with logging, we see a little bit of an increase, but then with industrialization, we see a big increase, but now we see a recovery. In Weber Lake, which has a ratio of watershed to lake area of 27, we're still seeing an increase, or at least a stable state in mercury levels, or at least loading to the lake. We're not seeing recovery, and that's because of all the mercury in the forest soils that are going into the lake. And so with this study, what we hope to eventually accomplish, among other things, is to understand forest management practices that maximize the retention of mercury that's coming from the atmosphere going into our forest soils. Maybe if we maximize retention, we'll only be delaying the problem longer. I don't really know, but that's something that we can study, especially in this proposal that we'll be writing to NSF for low temperature geochemistry. So as Luke mentioned, here's the Honeysuckle Creek watershed. What I've put here are permanent plots or Pearsall plots. Okay, and the design is really focused on pairing forest nodes of the wireless sensor network with these Pearsall plots. They communicate with this central base station that sends the data to the cloud, or eventually will. And we also have 3 stream nodes. So these, for the stream nodes, what we've done is we've put flumes on the stream so we can measure discharge. Eventually that will be, the discharge data will be sent to the base station and sent so we can all see it on our computers. And we'll also be putting water quality probes in the partial flumes. so we can have continuous data streams of water quality as well. I'm going the wrong way, sorry. A quick note is that we've submitted a proposal recently to expand our wireless sensor network to all of the biological station. It's a proposal submitted to NSF Major Research Instrumentation. We actually won the internal competition for the university, which increases our chance to NSF of 25%. Gives me a little bit of confidence, but not much. So if we get the funding, it will be to expand wireless sensor networks to all of the terrestrial environments on the different landforms, and then actually in our 2 lakes as well. If we get the funding, we'll be having workshops, so there can be input from the community actually for the design of the network. So hopefully I'll be contacting everyone about that. Okay. Honeysuckle Creek, Luke described it. It's a first order stream with perennial reaches alternating with intermittent reaches in uplands. So that means some places we see flow, some places we don't. And then basically near Burt Lake, where the ground is saturated, we see water flowing all the time. At the upper stream node, so that would be, well, in the upper watershed, what we see is base flow of 0. So it's really only flowing in the late winter and early spring. At the midstream node, the base flow is about 1 toilet flush per minute. It's not a very significant stream, and I'm not talking about the old toilets that really had a lot of water. I'm talking about the new low flow toilets. The lower stream node, base flow is about 2 to 3 liters per second. So this winter, I've actually hired Renee Varesh, who many of you might know. She spent time at the biological station. She's been going out to the stream and taking samples every week, even when it's terrible snow outside and cold. And what we see actually is when there's an increase in, well, discharge or flume height I have here, we see an increase in the discharge of particulate organic carbon and dissolved organic carbon. And along with that, we see an increase in the flux of mercury. I'm actually going to invite Tim to come up and talk for a minute or two. I can't seem to. Sorry. Talk about dissolved organic matter in the stream.
I'm going to need that mic, though.
Oh, yes.
Man, am I glad I didn't have to do all that background. Just bury my head in the lab and run analyses. So, we've got some interesting opportunities for collaboration here at Michigan Tech. One of the scientists that I reached out to is named Rose Corey, who's kind of recognized as a leading expert in the field of this EAMS spectroscopy. It's a really powerful method of sort of ascribing a fingerprint to dissolved organic matter. And the idea here is that we can use this collaboration in order to see where the carbon's coming from in the watershed and where it's headed downstream. We advance on this thing. So, oh, that's unfortunate. These are about the same thing. You kind of fuzz your eyes at these really complicated graphs. You can see it looks a lot like a fingerprint. That's really not a coincidence at all. We can use very complicated mathematics to deconvolve different features within these spectra, and each sample then ideally has its own composition of individual components or its own fingerprint. So we went and pulled some surface water samples and some piezometer samples, trying to see what the carbon looks like upstream, what it looks like downstream, and what it looks like offshore in Burt Lake. And, oh, they moved, didn't they, Paul?
They did.
The important take-home from this slide is that each region of this graph, if we just draw lines, can be ascribed to different characteristics or different molecular weights or sizes or oxidation states of the carbon. That's not what's important here. What's important is that we can take all these fingerprints, blindly feed them into a PCA model, and we'll notice that the different locations we sampled cluster. So way up here in this unfortunately faded blue is the upper Honeysuckle Creek carbon. That's taken basically right below a stand of aspen with rather sandy soil. Mid Honeysuckle Creek is at the bottom of the hill. That's composed of, notably, different carbon characteristics. And then at the very base of the hill, sort of at the mouth of the stream as it dumps out into Burt Lake, the carbon is unique there as well. But it doesn't look a thing like what's offshore in Burt Lake. So this paltry little trickle of 1 milligram per liter of dissolved organic carbon coming out of the stream appears to be transformed along the water course from top to bottom. And just traces of that are offshore. They don't really find their way out into the lake. It would appear that dissolved organic carbon really is not the main means of efflux from the stream. This is kind of a unique feature for something with 40, 50% carbon in the soil. Usually in a system like that, we would expect some of it to be dissolving, leaching away, exporting out into the lake. But in fact, it appears that particulate organic carbon is really the only way we're seeing any export from the system. So this is kind of flies in the face of what a lot of the wetlands literature expects us to see. Interestingly, we grabbed some piezometer samples right next to these sites, and the dissolved organic matter there doesn't in any way resemble what's in the surface water. So this is indicative of perhaps two isolated flow paths within the system. One that has upstream inputs that get slowly oxidized before they get dumped out in the lake, and some subsurface activity that is completely its own animal. We don't have a good handle on it, and I feel very strongly that we're going to need a lot more piezometers before we do figure it out. So if anybody would have any questions about what we've been up to in this fine system, I'd be happy to defer to the experts. Jane.
Why is there a lot of mercury in forests?
From 150 years of deposition from atmospheric deposition from mostly burning of fossil fuels. Places like Chicago where you're employed.
Yeah, but he lives in California.
I know it is.
He gets his paycheck from Chicago. Long history of Chicago politics. But, Paul, to follow up on that, you have the industrial area, but you have this pulse in the logging area. Is that because we were burning a lot of coal even while things were being logged? Or is that a land use spot, is mercury leaking out of the system?
I think it's mostly natural mercury, and that's just from erosion. If you actually look at on a flux basis, it doesn't look as important as what's coming down with industrialization.
Well, I think we're almost out of time. Is there one other question or two?
A question about the forest management practices that retain mercury. Status on that, or what do you find?
No, we don't know.
You don't know. Okay. But is that tying in?
That would be something down the road as we understand the watershed and then start to do plot scale manipulations or even whole watershed manipulations. This hasn't really been tackled very much, so we know that, say, forest fires will mobilize mercury to the atmosphere, or maybe even downstream, that cutting can mobilize mercury.
So I was wondering if that could tie in any of the forest management activities in the state.
Like a red pine harvest.
Yeah.
That's good.
I think that there might be a solid argument for the conservation of the cedar swamp ecosystems. It seems they hold a lot of carbon and do not release any of it. I wonder if maybe cutting might
from the results that we've had so far that mercury is attached to the particulate organic matter, and that flushes out during storms, basically from the wetlands. I think you could cut the entire upland, and if you kept the lowland in back, it wouldn't affect mercury flux out of the system. We should test it.
Thanks, Paul, Tim. Just to mention too, when we do the next burn, we're likely to do a cut without burning as well as a burn, so we could compare the results of cutting and burning with respect to mercury release.